that everybody recognizes the images from this telescope and recognizes its importance, to literally, everybody's life in the sense of inspiration.
And I should point out, by the way, that in my private office, just off the oval, I've got a picture of Jupiter from the Hubble.
"20 years after launching on a space shuttle and opening its instruments to the farthest reaches of space, NASA's Hubble Space Telescope has become synonymous with exploration, discovery, and even a bit of luck.
One of the things that Hubble has done is it really taught us something about our place in the universe and our role within it. We want to know, how did the universe start? How did our galaxy start? How did the Earth start? How did life on Earth start? And we also want to know, how will all of these things end?
When the telescope arrived, there was a lot of anticipation because there was so much extraordinary effort required at KSC in order to assure that the telescope was going to be able to maintain in the kind of environment that it had to be, and that meant a cleanliness standard that was extremely pristine, far beyond anything that we had ever launched before.
With years of design and construction behind it, the Hubble was sealed inside Discovery for liftoff. The Hubble Space Telescope flew into the national consciousness on April 24, 1990, inside the payload bay of Space Shuttle Discovery.
The launching of the telescope itself was a huge deal because the Hubble Space Telescope was long awaited, and it was supposed to be launched in the year that the Challenger accident happened.
Hubble was different from land-based observatories because it would operate from a point hundreds of miles above the distorting effects of Earth's atmosphere. Though its 94.5-inch mirror is small compared to those built on the ground, the telescope is huge by spacecraft standards. At more than 43 feet long, the telescope took up most of the shuttle's payload bay. But as large as Hubble was, it was sent up with a tiny flaw in its main mirror. It was an imperfection less than the width of a human hair, but it was enough to blur Hubble's images and leave the observatory's potential in doubt.
To find out 2 months after launch that it was launched with a misshapen mirror was crushing to NASA.
When the telescope had its spherical aberration and needed glasses, we had already built expectations to the point that they were expecting to see these kind of things right away, when in fact, even if the telescope had worked, where it's going to take astronomers a considerable amount of time to get some of that data and then to see what else Hubble was going to find that we didn't know about.
The telescope was quite powerful even with the flaw, but NASA knew it would have to fix it. So engineers set out to build Hubble a set of contact lenses.
So I think that was probably our biggest challenge, was to try to make people realize that these things were still going to happen. We just needed a little time to fix this problem.
Being able to restore the Hubble Space Telescope's observational capabilities was incredibly important to the agency, and they put together a great plan to do it.
Astronauts made 5 back-to-back spacewalks during the repair mission, a first. They spent more than 35 hours working on the telescope in the payload bay. The Hubble repair had effects reaching beyond the telescope's health as well.
This mission wasn't just about restoring the Hubble Space Telescope. It was about whether NASA had the capability to go off and build the International Space Station.
The problem was fixed to the extent that it never occurs to anybody to even think about it anymore, because the results are just so dramatic from the Hubble.
The first images from the telescope proved the servicing achieved its goal. The Space Telescope was free to look into the farthest distances ever seen, nearly as far back as the beginning of the universe. Astronauts made 4 more servicing flights to the Hubble Space Telescope to upgrade its instruments and replace critical components.
We did it in a way that we knew it was the last time we were ever going to visit the telescope, and we had to do everything to it that we wanted to do if we wanted it to last a lot longer. So that made it more complex. And when the mission was over, the feeling was we'd done it.
They had seen different worlds for the very first time through the eyes of the Hubble Space Telescope, and it's really expanded the general public's view of the universe, how the universe began, what the ultimate fate of the universe is going to be. It has ignited, it just has ignited the imagination of the collective American public.
The Space Telescope repaid each mission with more incredible views of space that all could see and appreciate. Hubble observations astounded researchers by showing the universe was not only expanding, it was speeding up.
Imagine your amazement if, when I throw these keys up, you would suddenly see these keys accelerating towards the ceiling. This is what we discovered. This was extraordinarily surprising, and it led to this notion of dark energy that is pushing on the universe to accelerate.
Once we began to get things back from Hubble, the scientists were beginning to see physical processes going on that they didn't really understand and hadn't been able to see before.
20 years after opening a new eye on the universe, Hubble continues to dazzle by reaching farther back in time and space.
The light that we're just now receiving from some of these galaxies and different objects show younger and younger galaxies and stars, the light for which, when they left that galaxy, the Earth hadn't even been formed yet. That's how far back in time Hubble is seeing.
We're talking about questions that a few tens of years ago we didn't even know to ask.
The whole thing is a very storied program from the very first launch until the last servicing mission.
There are more questions for astronomers to answer, and Hubble will remain in orbit to answer them for years to come.
I would say as a child I was always interested in all things kind of science related. I liked rocks, I liked dinosaurs, I liked planets. But my pivotal moments, I think I had two of them. And the first was the space shuttle program and Sally Ride, and the fact that, she was the first American woman in space, and I really wanted to do that. But the second was the Voyager flybys. And while I don't really have memories of the Jupiter flyby, I distinctly remember the Uranus flyby in 1986. And getting these images of these alien worlds, these funny moons, all different colors, all sorts of things going on there that we didn't understand. And really that cemented for me, I wanted to study space science. There was no other question, that's what I was going to do. So as a planetary scientist, I study the planets in our solar system, primarily the outer planets, and I'm interested in their atmospheres and how they work and what they can teach us as a laboratory for atmospheres all over the place, including the Earth. My background is a little interesting. I actually originally wanted to study Mars geology. But when I started my graduate school career, I had an opportunity to work on Jupiter data, particularly with Hubble, calibrating some of the early images before Hubble had its corrective optics, right before the Shoemaker-Levy 9 comet impacts into Jupiter. And then we had this great encounter where we had all these commentary pieces hitting in, but it was a new camera on Hubble after the corrective optics. So, wow, all these great new images. And I kind of got sold into, this is really what I want to do, study the atmospheres of planets.
Hubble Space Telescope's been looking at Jupiter for the past 25 years, and this particular image taken just a few days ago, we can see the dynamic cloud bands, all the swirling clouds and colors on Jupiter, of course, and the Great Red Spot. But we also see wave features and smaller storms in the atmosphere, so we're learning a lot about Jupiter's weather, basically, by doing these Hubble observations.
I would say I'm not really good at looking towards the future of envisioning exactly where I'll be in 10 years, but I want to see more missions to the outer solar system. I think we have a lot left to do out there, and I am looking forward to the day when we are ready to launch a mission to Neptune or even another mission to Saturn, and I certainly hope to be parts of those missions.
Catch these fuzzy images, and so he decided to categorize them and make a list so that he would never be distracted by them ever again. Thus began the Messier catalog. Hubble just today released its own album full of Messier objects taken by the Space Telescope, and we're going to talk about them here today with you. Make sure to send in your questions and we'll answer them at the end of the show. But I'm going to introduce you to some very special guests. So today we're joined by Michelle Fowler and Kevin Hartnett. Thank you both for being here today.
Hey, yes, great to be here.
All right, we're going to jump right on into it. Who is Charles Messier and why is his catalog so cool?
Well, Erin, you just said Charles Messier was an astronomer who was active in the late 1700s, and he was really interested in finding comets. He actually found many of them over the course of his career, but there were some fuzzy little blobs in the sky that looked like comets, but he could tell that they really weren't comets because they didn't move with respect to the stars. Right. Comets appear and disappear, and they actually move with respect to the background stars, but these little fuzzy blobs stayed right where they were. So he made a catalog of basically things to avoid that weren't comets. And the thing that is a wonderful irony is what he actually had discovered were some of the most dramatic and beautiful objects in the entire universe. Right. He discovered things like dead stars, or stars being born, or what we now know are very distant galaxies. So in fact, Messier found some of the most fascinating things in the sky.
Yep. What's very interesting is the first object that we'll talk about, the Crab Nebula. He was looking actually for the return of Halley's Comet himself, which was predicted to show up in the constellation of Taurus in that period. And so he was scanning to find Halley's Comet and came across this object we're going to talk about.
So the catalog is just numbered basically in the order that Messier discovered these things. And so we're going to start with M1. And just like Kevin said, M1 is something called the Crab Nebula. So we actually have a depiction here of where the Crab Nebula is in the sky and a little bit about what it looks like. So you can see it's actually here in the constellation Taurus. It's going to be honing in on that. And as this begins to pan in, look, there's a fuzzy little thing there. And that's what he saw, and that's what he thought might be a comet. But as we pan into it even more, you see that there's wonderful dramatic structure. And what this turns out to be is an exploded star. It's what we call a supernova remnant. So there was a star long ago that exploded, and it actually spread its material over hundreds and hundreds of light years. And in the middle, there's the dead core of a star called a neutron star. Neutron stars are amazing. They have the density of Mount Everest pushed into every teaspoonful of material. And they actually rotate hundreds of times a second. And I remember that you actually knew what year the star exploded.
Yes, so historians have figured out that this is associated with the Chinese sighting of a guest star, they called it, that was visible, so bright it could be seen during the daytime, and that was 1054. So we're very sure when this star actually exploded.
Now, Kevin is an amazing amateur astronomer. He actually takes pictures of these objects with his own telescope. So should we go to some of the images that you've taken yourself?
Sure, why not? In this case, I don't have one of M1. We'll see others, but I wanted to show you both this chart and where M1 can be found. Do you see the constellation of Taurus here? This little cluster of stars called the Hyades is V-shaped, and it marks the horns of the bull of Taurus. He's up and to the right of Orion, very easily spotted in the winter sky. And you take the lower horn and look at it with a telescope, and you're sure to find M1 if you just sweep around the field of view with that star in it, because it's very close to that star named Zeta Tauri. So I want you to know that in the Hubble catalog that's been released, we have a star chart like this for every Messier that's in the catalog. So even if you don't know anything about the Messier objects, you'll know basically where to find them in the sky, what season to look for them in, what constellation they're in, and we also tell you in the album what telescope is a good one to look for this object with, and what time of the month or what month of the year you should be looking for it.
So keeping with the theme of dead stars, there's another one of my Messier objects that's one of my favorites. It's called the Ring Nebula. And so we talked about M1 being the first one. This is all the way at M57. Now the Ring Nebula is in the constellation Lyra. And this is actually a different sort of dead star. The first one we saw exploded violently in a supernova. This star is basically gently unraveling itself into space. It was a star that was more about the mass of the sun. It's dying and actually losing shells of gas around it. And in the middle, there's the remnant of this tiny little star, which is now cooling off and basically dying. So the Ring Nebula is a beautiful, beautiful object, and you can see some of the complexity that the Hubble Space Telescope discovered when it actually took many different visuals of this Ring Nebula. So the thing that I really love about the Ring Nebula is it's not very easy to see in a telescope. You have to use a special technique to see it. So tell us a bit about your observations of the Ring Nebula and how you see an object like this.
Okay, sure, I'd be happy to. It's one of my favorites. It's a great summer favorite for amateur astronomers. It's high in the sky, and it's fairly easy to locate in the constellation of Lyra. But as Michelle said, it's small and a little bit hard to find. And when you put in an eyepiece that has more magnification, it dims, and it gets a little tricky to see, especially the hole that's in the center. What you have to do, and this is a trick that we amateurs use, is look to the side of the object, because the edge of your eye is more sensitive to light than the center is, oddly enough. You have rods and cones in your eye, and the rods are along the edge. So at night, your peripheral vision is better than your center vision, and you can see things that move. So as a trick, we get the object in the telescope and then look to the side of the object and wiggle the telescope a little bit, and you can actually see it better when you do that. Especially the hole in the middle. It looks like a big smoke ring in the sky when you use those tricks. Now you won't see the center star because that's pretty faint, and although I took this photo with just general DSLR and a modest telescope, the camera is more sensitive than your eye, and so it can pick up on the star. You'd need probably a 14-inch telescope to see that star.
So we're going from the theme of dead stars to something now very different, and that's the birth of stars. Messier actually discovered things that represent all the different phases of the life cycles of stars. So we're going to start talking about young stars.
Yeah, and while we walk over to talk about the young stars over here, I wanted to remind everybody to continue to send in your questions. We're getting some really great ones. We're still here at Goddard Space Flight Center talking about Hubble's Messier catalog, and now we're going to be talking about dead stars. So take it away. I'll get out of your way.
Well, that's right. These are stars that are being born. The next object we're going to talk about is one of my favorites in the sky. It's like an old friend returning every time the fall sky rolls around, and that's M42. This is the Orion Nebula. And as you can see in this wonderful animation, what the Orion Nebula really is a giant cloud of dust and gas. And inside it, there are stars forming that are lighting up this cloud. And there are actually 4 very bright stars at the very heart of the nebula called the trapezium cluster. And these stars are actually larger than the sun, more massive than the sun and brighter. And the light from them is lighting up the whole area that we know of as the Orion Nebula. To me, this is one of the most beautiful images ever taken by Hubble. It's not only beautiful, but it's very dramatic when you think about this is a cloud of dust and gas, many, many hundreds of light years across. And inside it, there are dozens, if not hundreds, of new stars forming right now. So this is a beautiful object, and I have to say that the image you took of this is spectacular. I mean, you are an amazing astrophotographer. Let's take a look at what you got with this one.
Well, it is one of my better efforts, but they're all work, and I want to really communicate that taking pictures is another aspect of astronomy that's enjoyable, has its technical challenges, but I've spent most of my life observing these things with binoculars or a telescope, and it's as much fun. It's probably more fun than trying to take pictures of them, which is just hard. So here you see an image of Orion Nebula, and I want to point out the contrast between this one and this one. It took Hubble about 500 different pointings, mosaics stitched together to form this image. Because Hubble zooms in, it has such high magnification, it zooms into a smaller part of the object. This could all fit in the field of view of my telescope. When you're looking at this object just with a telescope and not worried about taking pictures, you want to look for it beneath the 3 stars that form Orion's belt, the sheath for his sword, if you will. Right in that area, from a dark spot, you can see a faint cloud. And put a telescope on it, and you can see there, right there is an image of where M42 is. Again, this is on our website, so you can find these for all the Messier objects there. But you put a telescope on it, and you can see this trapezium, 4 little stars in a trapezoid shape, and enjoy the dark and light bands of this nebula. It's truly spectacular.
Messier actually found a number of examples of young stars. In the case of the Orion Nebula, the stars are still forming in this cloud of dust and gas. But then there are other stars that are a little farther along that have actually moved out of the clouds they were born in. And in many cases, just the radiation and also the particle winds coming off these bright young stars blows away the cloud. And so the next thing we're going to is an example of a young cluster of stars. Stars that have all formed probably in the last at least tens of millions of years. It doesn't sound very young to us, but for stars that they are. And this is a cluster called the Pleiades. And the Pleiades is a wonderful thing to see in the autumn and winter sky. It always is wonderful for me because I know that wonderful, beautiful autumn sky is rolling around. These images look very different. So here's the image that you took of this young cluster of stars. And in fact, the Hubble image is has so much resolution and so much focus, it's only a tiny part of your image here.
Right.
So compare the Hubble image that we have here with what you were able to see with the Pleiades.
So it's a very tiny portion. The Pleiades is a naked eye object, and it's somewhat like 3 or 4 times the size of the full moon. So it's very big on the sky. This image taken by Hubble of part of the gas and dust surrounding these stars is right in between this bright star called Meropa and these two little stars next to it. So it's a very, very tiny portion of the actual Pleiades. Pleiades is also known as the Seven Sisters. A lot of people mistake it for the Little Dipper because it has this dipper shape. And with your eye, you really only see 6. You know, there's this legend of the missing Pleiad because you don't see 7. But this cluster is also known in Japan as Subaru. And so when you look at the logo on the back of a Subaru, you're looking at this star pattern. Most people don't know that. So it's a very, very beautiful cluster, and best appreciated actually in binoculars or a small telescope where you can see just these diamonds on a black background.
So we're talking about families of stars, and the type of cluster that the Pleiades is something called an open cluster. And these are stars that form relatively close to each other in one of these big clouds. But the sun was probably in a cluster like this billions of years ago. But over that time, we've been around the galaxy so many times that just the gravitational interaction between the stars has peeled off all the other members of our star cluster. We don't really know where in the sky our brother and sister stars are. So an open cluster is a family of stars that all form together. And actually, we're going to go over and talk a bit more about some different families of stars now.
Yeah, and once again, while we're walking over, I just wanted to remind everyone to keep sending in your questions. I'm getting some really, really great ones. And we're here at Goddard Space Flight Center talking about Hubble's Messier catalog. So continue sending in your questions, and I'll let you guys talk about clusters.
Thanks, Aaron.
So here's another example of an open cluster. This is M11, which is also called the Wild Duck Cluster. And as I said before, open clusters are stars that formed together relatively recently in the last millions or tens of millions of years and are slowly peeling apart over time. So this is another one that you have a very different image. Hubble is taking sort of a picture here of the heart of this cluster, and then you have a picture of the larger cluster so people can see that.
Right. Neither one of them look much like a wild duck, do they? But if you had a small telescope or a pair of binoculars and looked at this object, which is in the summer sky in the Milky Way, you will see a V-shaped grouping of stars. The brighter stars are V-shaped and reminded the early observers of a flight of ducks or geese that are characteristically, you know, flying in a V. When I look at this, and this is one of my favorites too, you notice right away, and so did Messier. He wrote in his catalog about this, that there's a very bright star in the center of the cluster. Hard to make out here because it just gets lost with all the others. But it's very, very noticeable when you look at it for the first time in a telescope. This amazing grouping of stars and this one bright one right in the middle. Now I find this cluster is particularly fun to look at in higher magnification, and I like to use a zoom eyepiece. So I look at it at low magnification and the stars are really tight, and then as you twist the eyepiece, it zooms in and you see just hundreds more. It's a remarkably beautiful open cluster, and there's something like, hundreds of stars in the cluster.
That's right. Now, an open cluster can have dozens or hundreds of stars, but there are actually much larger star clusters as well. And certainly the largest ones that are in our own galaxy, the Milky Way, are called the globular clusters. And we have an absolutely spectacular picture of a globular cluster here. This is the globular cluster M15. So this is the 15th thing on the list of things that were not comets. Right. And this is actually a cluster of stars that contains millions of stars. Now, astronomers believe that globular clusters are actually ancient clusters. They probably formed very early on in the lifetime of our galaxy. And if you think about the Milky Way galaxy, we live in a spiral galaxy that's kind of shaped like a frisbee. It's a disk of stars and gas and dust. But the globular clusters actually orbit around the entire galaxy, almost kind of like a swarm of angry bees. They're going all different directions around the Milky Way. And in fact, globular clusters were one of the first ways that we discovered our own place in the Milky Way. It turns out that we're nowhere near the center of the Milky Way. We live out in the suburbs, about 3/4 of the way out into the disk from the center. So that's a long way from the middle of the galaxy. And all of these globular clusters orbit around the center of mass of our galaxy. So astronomers a long time ago realized that most of the globular clusters were in one half of the sky, and there were fewer on the other half of the sky. And that's because we were looking from a vantage point of being very far out from the center of the galaxy. So whenever I see globular clusters, I'm really aware of the place, the role that they had in actually giving us a map as to where we are in the galaxy.
And it's really a good thing that we're not on a planet inside a globular cluster, because we wouldn't see much of the sky at all, right? Also, it would be like daytime all the time.
You just look at all of those stars packed into that little area.
Yes, so it's very good for observing that we are where we are.
So you've got another great image here.
Yeah, so this image is fun because I took it 2 nights ago, right? And I took it with a very small telescope. But it's in the constellation of Pegasus, the flying horse, which if you go out into night sky, will appear as a square. They call it the square Pegasus, very prominent square in the sky. And I like to consider it like a baseball diamond because it's oriented that way. And this object is located off first base. So you go up to first base and there's an L-shaped string of stars. It's right at the tip of the L. Very easy to find.
Right there.
There you go. Yep.
So we've been talking about families of stars, the star clusters, and in fact the largest families of stars in the universe are the galaxies. And these are families of stars that include hundreds of billions of stars. So let's talk a bit about some of the galaxies that we're looking at.
Yeah, and actually while we walk over to the biggest screen in the room, we'll talk about the biggest objects, right? So I just wanted to remind everybody once again that we're here at Goddard. We're talking about Hubble's Messier objects. And please continue to send in your questions. We've got a ton of good ones. And I'll let you talk about galaxies now.
Sounds good, yes. Right, so we're going to end with looking at some of these beautiful spiral galaxies. And the first one we're looking at is something called the Whirlpool Galaxy, which is known as M51. And the Whirlpool Galaxy is a spiral galaxy about half the size of our own Milky Way, and is actually at a distance of about 23 million light years away. So you can see here in this beautiful Hubble image the detail on the spiral arms of this galaxy. The dark areas are actually lanes of gas and dust where new stars are forming inside that right now. And in fact, whenever you see red areas along the spiral arm, that's active star formation. That's where young stars are still embedded in the dust, and they're actually lighting up the dust and making it glow red. It is an absolutely beautiful spiral. So the thing that's amazing about this is it actually looks quite different through a telescope. And some people might be disappointed, but I still think it's a wonderful thing to look at. So tell us a bit about what it's like to observe a beautiful galaxy like this.
Okay. I'll tell you, it's fun to glimpse these things, even if you're not seeing them particularly clearly in the night sky. There's a connection you feel with the universe by looking at the light of these things with your own eye. So just like Messier would have seen this, it was a smudge. But now you know what it really is. And that's electrifying. If you're at night searching for these things with your telescope and finding it and realizing what you're seeing, there's nothing really quite like it. So Messier would not have seen the spiral arms because you need a large telescope to do that. And his telescopes were not very good. They weren't even made of glass. The ones that we use now with mirrors, the mirrors were made out of metal back then. And we've looked at these globular clusters. In M15, Messier noted he didn't see one star in that globular cluster that we now know has millions of stars. So his view was very, very different. But this is an image I took. It took about 4 hours to lay up that image. In a second, I'll show you what one little frame looked like. But this object was not seen by Messier at the time. It's a neighboring galaxy. He only saw the very core of this, and it looked like a little blob.
So the thing is that even if if your telescope image doesn't look like this, it's still wonderful to think that the light you're looking at, even when you see a little smudge on the sky, in this case is 23 million years old. 23 million light years away means the light took that long to get to us. So when you see this beautiful galaxy as just a smudge in the sky, that light left long before there were humans on the Earth. So you mentioned you're going to show us, so this is what you might see through even a large telescope.
Yeah, well, this is taken through an 8-inch diameter telescope, and it took, I'm trying to remember now, about 3 minutes or 4 minutes to lay up this particular image. And you see you get all the light pollution, right? The sky glow in the background too. And the trick that amateurs use is to stack all these up, line them all up. And so I took whatever 4 hours of 3-minute exposures, and you can get software free off the web now to align them all and stack them up, and then you learn some about processing. Honestly, although I don't want you to think that you're going to see these marvelous images, the pictures like from Hubble or even my telescope, by looking through the eyepiece, it is encouraging, or it should be encouraging to you, that I've only been at astrophotography for maybe 4 years with a digital camera, and so you can learn very quickly. There's a lot of resources on the web, but start with the Hubble site. You can find out where the Messiers are in the sky, and what instrument to use to look at them. And once you get more familiar with the sky, like I've done for over many years, then dabble in astrophotography.
So we're going to wrap up our catalog of the Messier objects with one of the most beautiful things in the sky called the Andromeda Galaxy, and this is M31. And I have to say, Kevin, this is your image. This is absolutely spectacular. The Andromeda Galaxy is a galaxy very much like the Milky Way. It's at a distance of a little bit more than 2 million light years away. And the thing that's amazing about the Andromeda Galaxy is that edge to edge, this is as large on the sky as 3 full moons. Think about lining 3 full moons up across that galaxy. So at night when this thing is up, there's this giant galaxy actually covering a fairly large part of our sky. But the reason you don't see it is it's very faint. And in fact, Messier could only see the very, very central part of the galaxy. But there's other objects in here as well that Messier saw, in this gorgeous image you took. So tell us about that.
Well, would that we all had eyes to see this thing in the sky, hanging there in the autumn sky, as big as 6 full moons across, right? It's just an amazingly big object, but it's faint because it's a long way away. So when you look at this in a telescope or with binoculars, in fact, you can see this object with the naked eye from a dark place. You're really only seeing the very bright core. But that's what you'll see in a scope or binoculars. Very fun to see. I remember dragging my whole family out when I was maybe 15, and it was in the winter. And I said, now that I found it, you have to see it. So it was like 20 degrees outside. Drag all my sisters out to see this thing because it's a classic. It's very spectacular. This object, Messier also found, probably within the same night that he looked at M31. This is called M32. Again, very easy to see because it's so close to M31. And it looks like a slightly out of focus star. A little harder to see is this one down here, a companion galaxy, now known as M110. And you have to use that little trick I mentioned earlier, looking to the side of M110 to see it more clearly. I like to take people out and show them Andromeda through the telescope, because it's very easy to see this, a little harder to see this, and they have to really work to see M110. So it's a great learning experience.
So going to the Hubble image of Andromeda, this is something that's kind of mind-blowing. Hubble is so powerful, it can actually see the individual stars in this galaxy 2 million light years away. Now, this galaxy contains hundreds of billions of stars. And when you look at this image, there's kind of a graininess to the image, and that's real. These are all individual stars that Hubble can pick out. Now, the amazing thing is it took Hubble over 400 different pointings to stitch together this giant mosaic of Andromeda. And in fact, Hubble only had the time to image about 1/3 of the galaxy. So think about that. More than 400 Hubble images all put together in a mosaic to cover just about 1/3 of the Andromeda galaxy. So it's an amazing thing to see and an incredible Messier object. So hopefully in talking about these wonderful objects you can see in the sky, things like dead stars, stars being born, galaxies, star clusters, you might want to go out and actually look at them yourself. And this is where Kevin is the expert. He's going to talk to you a bit about what you can do to actually go out and make your own Messier catalog. So you've brought some telescopes here. Let's go over here and take a look at this.
So I should probably start here. Because from a dark sky, you can see most of the Messier objects with a good pair of binoculars. From the Washington, D.C. area, maybe a quarter of them. But if you're out in a dark spot, you can see many of these. So get yourself a star chart like this and find them, or use the star charts that are on the Hubble site, and you'll know where to look. It's good to use a set of binoculars at night that's one like this. This is a 10 by 50. 10 is the magnification. 50 is the size in millimeters of the glass up front. Most of us have 7 by 35s at home, and they're great for terrestrial viewing, looking at things in the yard or whatever. But you want a little more power, and you want to gather more light because the stars are faint. So you want this lens to be as big as you can hold steady. That's the other caveat, right? So if you get too heavy a binocular, you can't hold it steady and you won't get a very good view. So just two other representative scopes. You might be fascinated to know that the beautiful picture of Andromeda that I took and the one of the Pleiades was taken with a scope almost exactly this size. It wasn't this particular one, but I had it mounted on the back of a larger scope and a more expensive mount that was tracking the stars because, again, had to lay up these time exposures. But you can enjoy the Pleiades and the Orion Nebula and M31 all as beautiful objects in a scope this size. Our website says for each individual object, it's best seen or can be seen with a large, medium, or small telescope. This is what we mean by small, up to 3 or 4 inches. Medium would be more in the class of a 6 to, say, 10-inch diameter telescope. The size of the lens, again, is the size of the, it's what's collecting the light. So think of it as your eyeball. Imagine your eyeball being 8 inches wide. You collect a lot more light. And then larger scopes, which didn't have room on set to bring in here, can be 10, 12, 16. Some amateurs have 20-inch telescopes, great big things. But they get obviously difficult to move around. Each has their own price range and pros and cons. Read up on a website that describes telescopes before buying one. And really, I recommend learning your constellations, finding the Messier objects with a binocular, and then stepping up as your interest continues. Here's a zoom eyepiece that I was mentioning before. So you just twist it and it magnifies, so you don't have to keep reaching for different eyepieces. If you do want to do that, there's many different types, and it just makes it easier. I find it easier to just zoom in. Interestingly, Charles Messier, he looked through about every telescope he could get his hands on, and they weren't very good. And they didn't have eyepieces. The eyepieces they had weren't replaceable, I should say. They were a fixed magnification. So interesting difference.
Before we go on to some questions from the audience, actually the question I have for you is how many Messier objects have you personally seen?
Oh boy. Yeah, so I've seen just about all of them. We didn't talk about it tonight, but there's a large group of galaxies in the constellation Coma Berenices off the tail of Leo and next to Virgo, where there are just literally scores of galaxies. Some of them are Messier objects. Many of them are not. They didn't make his list. So I've looked at that cluster, and when you look through the field of view, you might see 2 or 3 Messier objects, but 2 or 3 that are almost as bright that he missed somehow. And so I've seen them all. I haven't cataloged them all, but I'm starting to do that afresh now. It's kind of a bucket list thing for me. If you write down the day and time and scope that you use and some details about the sky, and send that log to the Astronomical League, you can get a certificate, which is really cool. It'll say you've seen all the Messier objects. So I'm now logging them all. I've probably seen them all, but I didn't log them all.
Well, excellent. So, I think before we go, we have some time for questions.
Yeah, we do, and it seems like we have a couple Messier collection hopefuls in here. We have one question asking, what is the best kind of telescope for a beginner? While we're over here, we might as well start with the telescope questions, yeah?
Yeah, so the best answer I've heard to that question is one that you will use, okay? So it can't be too heavy, it can't be too complicated, it can't be too expensive, right, if you're just a beginner, because you want to get your feet wet, right? And realize, hey, I really can find things and enjoy them, and then move up from there. So I find ones that have this style of mount helpful. It's called a azimuth and elevation, and so it's very intuitive to just swing it around and bring it up and look for your object in one of these types of telescopes. So I think this is a good choice, not maybe this big, but an azimuth elevation kind of mount on the telescope.
And then similar, we got a different question from someone else asking what are the best kind of binoculars for backyard astronomy?
Yeah, well, again, I would say shoot for something that's like a 10 by 50, like these, and not too heavy. If you get much heavier than this, they sell stands that you can put them on, but you'll want something to steady them. So I think a 10 by 50 is a pretty good size for most places.
That's always my problem. Is I love using binoculars, but it's hard to keep them steady in your hands. So people have techniques like, you know, resting your knees on your elbows on your knees and steadying
Right.
that way, or actually going up against a wall. That's one of the harder things, is learning to steady the image.
Right.
Speaking of images, maybe we'll come out here so we can see some more of these images in the background while we take a few more questions. Watch your step. Kelly wants to know what causes new stars to move away from the cloud that they were born in?
Well, there's a lot of reasons for this. I mean, there's actually intrinsic movement of the stars, that when stars form, they actually pick up angular momentum. They begin to spin, and the clusters of stars spin in different ways too. And over time, this can actually spin some of the stars out of the cluster entirely. But the other thing to remember is that star clusters never live just by themselves. We go around the galaxy. Right now, we're actually flying around the center of the Milky Way galaxy at about 500,000 miles an hour. Good thing we don't actually feel that. Right. And as the sun moves around the galaxy, it has very gentle gravitational encounters with other stars. Over billions of years, over many passes around the galaxy, this actually spreads the cluster out. And so we've actually left probably some of our sister stars way on the other side of the galaxy. The star formed right near us, but now it's 100,000 light years away. And that's just the regular gravitational attraction of the different stars as we move through the galaxy.
Great. It seems like these clusters kind of resonated with people. Someone else wanted to know, how far away are stars in a cluster?
Oh, now that's a very interesting question. I don't have an exact number for some of the clusters that we've been showing you, but as Kevin mentioned, if you were in a globular cluster, if you were actually in a planet around a star, in the heart of a globular cluster, the night sky would be brilliantly bright. So the closest star to us is about 4 light years away. And in the heart of a globular cluster, it'd be a lot closer than that. I don't have an exact number, but I do know the night sky would look a lot different.
4 light years is actually a long way,
yeah.
Right? And so if I've read that if you considered the volume of sphere, 4 light years in radius, in some of these globular clusters, there can be as many as 10,000 stars within that sphere. And so imagine being on a planet around one of those. It would be just dazzling.
Yeah.
And then another question, this one looks like it's specifically for Kevin. How do you deal with light pollution?
Yes, well, I cry a lot, I guess, is the answer. If you have a portable telescope, right, which some of mine are, you get to a dark spot, and that way you can just enjoy the night sky and find things easier. Taking pictures, see, is one of the strategies that I have to fight light pollution, because you can play tricks with a digital camera. Digital camera is very, very sensitive, if you've seen in these images. And so you could play these tricks about stacking up photos and processing them and get these amazing results. I live north of Washington, D.C., where it's very, very bright. And yet, you can play these tricks with a digital camera. Some of the same tricks Hubble plays, actually. Taking an image and then basically covering the shutter and putting a black cover on the telescope and taking another image. You say, why would you do that? You record the noise in the camera, and then there's software that you can use to subtract off the noise. And so this is a way to fight light pollution. You subtract it off with a digital camera. Can't do that with your eye. But Hubble plays that same trick, not to fight light pollution so much, but just to get that noise that's inherent in the camera because of its thermal qualities, and subtract that out.
It's amazing to me just how much we're missing with light pollution. I mean, I think that the most beautiful sky I ever saw was when I was in Chile. I was in the Atacama Desert where there were no lights around at all. And somebody actually pointed out the Milky Way was so bright overhead, it actually was making me cry. It was so beautiful, I was getting tears in my eyes. And I actually looked down at the ground and someone pointed out that I was casting a very dim shadow on the ground. But there was no moon out that night, none of the bright planets were out that night. That was actually a shadow being cast by the Milky Way.
It's very
That's how bright the Milky Way can get. So, I mean, get yourself to a dark sky area if you possibly can.
Wow, that's crazy. So we got a question about Hubble specifically. How does Hubble take so many sharp images when it's moving so fast?
Pointing. I think I'm going to lead this to the Hubble operations manager. Absolutely.
That's for you, Kev.
Yeah, so you don't think about it much. That would be more of a problem if the stars were closer. But they're so far away that the light that's coming anywhere near Earth is coming in parallel beams. And so, yes, Hubble's moving around the Earth, but it's still seeing these parallel beams that come from these different distant stars. If an object were closer, like the moon, you don't see many Hubble pictures of the moon, do you? See, Hubble was never designed to look at the moon. Now we've, over the years that Hubble's been operating, we now have modes that can, but they're very seldom used because you have what they call a parallax problem. The moon's too close and Hubble is moving too fast. That light beams aren't coming to you in a parallel fashion. And so the secret is the stars are so far away.
Wow, that's fascinating. So someone asked, what is the best telescope for astrophotography?
Okay.
I don't know how to answer that question. That's why I'm asking you.
There's different types of targets, right? There's what we've been calling, these ones would be classified as deep space objects, DSOs. And there's also like the moon and planets. You would want a different type of telescope to do lunar and planetary work than you would for deep sky objects. And so that's part of the answer. For deep sky objects, I think most websites that I would go to, people more experienced than I at this, would say get a medium-sized refracting telescope. That's the type that has the lens up front with fairly short focal length, and that will probably do the best for you for these things. Lots of reasons why, but those kind of telescopes can range from the $600 one that I bought to $6,000, so you kind of go with your budget too.
And so much of it appears to be in the way you process the images. I mean, like your image of Andromeda was spectacular. I mean, I remember when I first saw it, when we were rehearsing for this, I said, that's something that like the Mount Wilson telescope would have taken 100 years ago. That would have been like the best astronomical image in the world. But here you did this out of this small scope.
Yeah, there it is. Right here.
And so that has to do a lot with what you do with the imagery afterwards, too.
So true, yes. The more you stack, the more signal to noise you get, and the more you learn about Photoshop and these other processing techniques, just the better you get at it. And I really consider myself a baby at it. This, again, was about a 4-hour exposure, and many times more than 4 hours in processing.
And you've only been doing this for about 4 years.
Yeah. Again, it's because there's so many resources online. We're bringing you the Hubble Messier catalog online with all its information. There's lots and lots of helpful resources out there about astrophotography.
The Messier catalog is such an inspiration to me because, sort of wrapping it all up again, we talked about avoiding these things that aren't comets, but instead it turns out to be the catalog of wonders. I mean, everything from dead stars to baby stars to these vast galaxies that you took a picture of. Well, in some strange way, we have Charles Messier to thank for all that, even though it wasn't what he was looking for.
Yes, he found 13 comets on his own, remarkable for the instruments he had, and operating from the center of Paris. Can you imagine it? In an observatory there. And he co-discovered 7 others with his friends. So the man found 20 comets in his lifetime. Very, very remarkable for the instruments that he had and the place that he was doing it from. Try to even discover one from the center of Paris right now. Pretty hard to do.
Yeah. Are you ready for another question?
Sure.
Alejandro wants to know, what are your favorite locations for stargazing? I guess I can ask both of you that question.
Well, I just mentioned the Atacama Desert, but that's kind of hard to get to. So, you know, it is amazing to me how much you actually can see from a relatively dark backyard. If you can get yourself to an area with a nice clear horizon, you know, I've seen comets through small binoculars. You know, I've seen small telescopes where you can see the rings of Saturn. Saturn in particular is an object, I mean, obviously a lot closer to us than the Messier objects are, but this is one of the things where if you're a little disappointed by the Andromeda Galaxy just being a smudge, when you see Saturn and its rings right there in front of you, and the moons of Saturn as well, that's something that just floored me the first time I saw it. It looked like somebody had taken a picture of Saturn from a textbook and just kind of pasted it on the end of the telescope. So some of these objects are actually very easy to see. They're very bright, so you don't need a dark sky to see them.
Yeah, that's right. The moon and planets, in even a very modest-sized scope, can be a unforgettable experience. As you mentioned, seeing the rings of Saturn, I've been at so many star parties, we call them. We have telescopes out and have fun with the heavens. It's so fun to see people see the moon or the planet Saturn or Jupiter with its moons and bands for the first time. They never forget it. I never forgot it. That's really what got me into astronomy many, many years ago, seeing Saturn. There's a connection with the universe that you feel, and it's really unforgettable. But where would I go? Around here, I have a brother-in-law that lives down in Virginia in the mountains, and so that's a good spot to go. And the Eastern Shore is a pretty good dark spot with nice horizon, so you can see things from horizon to horizon. But if I were going to pay money and go someplace, it would probably be Chile or someplace like that, or Hawaii, to be on the top of a mountain where all the other great telescopes are, and observe from there.
And one thing I have to say is take advantage of your local amateur astronomy societies, because pretty much wherever you are in the United States, there's a local club where if you don't know what sort of telescope you'd like, if you don't know how to use a telescope, if you don't know where the nearest dark sky areas are around you, your local astronomy club will know these things.
That's right.
And they are an incredible resource. And as a professional astronomer, I would go to these large observatories and people would type the coordinates into computers and I would make my observations. I often feel that the amateur astronomy community are the real astronomers. They're the people that really know the sky like the back of their hand.
Right. Amateur astronomy groups will also love to show you their telescopes. And so you can try before you buy if you go to a club. And that's also helpful.
Great. It's kind of like asking someone about their job, asking someone about their telescope. They can talk for days and days, right? So unfortunately, we only have time for one more question. We're going to keep answering some of your questions on Facebook as they're coming in later on, but unfortunately we only have so much camera time. So one more question. What is your favorite object you viewed through a telescope?
Oh, it's like choosing between your children.
Yeah.
Oh, wow. Okay, so I guess, well, we just mentioned Saturn. So, I mean, I think that probably actually is my favorite. In the southern sky, there's something called the Carina Nebula. And the Carina Nebula is an area where you can see star birth and star death all happening at once. There are young clusters of stars, and then there's a star called Eta Carina, which is actually very close, we think, to blowing itself up in a supernova explosion. This part of the sky has these vast bands of dark dust and bright gas. And I have to say, those are some of the things that I've seen with my own eyes when I was living in the southern hemisphere that just blew me away. I mean, this is probably the closest thing I've seen with my naked eyes looking through a telescope that actually looked like a Hubble image. So Eta Carina would have to be one of my favorites.
Yeah, and for me, it is like deciding between your children, I guess. I really love to look visually at M11, that wild duck cluster, because when you first look at it in the scope, you can imagine how Messier didn't see any stars in it. They're very, very close, and yet you zoom in, and it's almost like the fly-throughs that we saw. It turns into something else. And it's in the heart of the Milky Way, where it's surrounded by hundreds and hundreds of stars to begin with. And so I don't know how to describe it. It's just beautiful. I could look at it for a long time.
If we don't know how to describe it, you need to try it yourself.
That's right.
So get out there and find the Messier catalog yourself and enjoy the absolutely beautiful images that the Hubble Space Telescope has made of these objects.
Absolutely. So like they said, if you want more, we've got the catalog up on our website, nasa.gov/Hubble. And if you want to know anything about Hubble at any time, you can follow us on Twitter at NASA Hubble. Thank you both so much for being here. And thank you all for tuning in to us. And we'll see you next time.
Hey, great to be here.
Bye.
Thank you. Bye.
Jupiter's moon, Europa, an icy world that's thought to have a subsurface global ocean of water. That same ultraviolet images of probable plumes on this icy moon. While these plumes seem intermittent, they appear to have repeated in the same location. Pieces of the puzzle of what's going on with Europa are continuing to come together. When the Galileo spacecraft was orbiting Jupiter in the late 90s and early 2000s, it gathered data to build a thermal map of Europa, and it appears the water vapor plumes Hubble is observing correspond with a relatively warm region on Europa's southern surface about 200 miles across. This thermal anomaly the Galileo spacecraft observed suggested geologic activity was happening in this location, a conclusion now further supported by Hubble's recent observations of water vapor plumes. This phenomenon may be similar to what the Cassini spacecraft has seen at Saturn's moon Enceladus, where there are also water vapor plumes associated with warm regions on the moon's surface. The warm spot on Europa has a couple possible explanations. Perhaps this location is warmed by liquid water a mile or so under the surface, pushing up through the cracks in the ice. Or perhaps the fine mist that's falling from the water vapor plume changes the structure of the surface ice grains, allowing them to retain heat longer than the surrounding landscape. Now that Hubble has shown Europa probably has water vapor plumes associated with warm spots on its surface, this information will be used for planning NASA's upcoming Europa Clipper mission. Europa Clipper will be able to take up-close observations of these probable plumes Hubble identified, and will be equipped with instruments that can detect any additional warm spots and water vapor plumes. This will provide insight into Europa's chemistry, geology, and potential conditions for harboring alien life.
Hi everyone, welcome to today's live stream. My name is Elizabeth and I'm here on behalf of the Hubble Space Telescope outreach team at NASA's Goddard Space Flight Center. Today we're so excited to share newly released Hubble images of 30 beautiful celestial objects in honor of Hubble's 30th anniversary year. We're live now on Facebook and YouTube, so feel free to comment your questions and we'll try to get to them later in the show or afterward on social media. So this has been quite the landmark year for the Hubble Space Telescope, which has been orbiting above Earth's murky atmosphere for 30 years, since April 1990. Hubble continues to bring us stunning discoveries and images of our universe. Joining me today, we have Hubble's Senior Project Scientist, Dr. Jennifer Wiseman, and Deputy Director for Science Communication, Dr. Michelle Thaler. Let's go ahead and take a look at some of these new images now. All these objects belong to something called the Caldwell Catalog. These images are really gorgeous, aren't they? So the Caldwell Catalog includes galaxies, star clusters, and nebulas, which are clouds of dust and gas in space. Let's go ahead and jump right in. First up, we have an image of Caldwell 45. Caldwell 45, this is a gorgeous spiral galaxy, and it has something called nuclear rings. So Jennifer, can you explain what that means?
Sure. So this galaxy, just spectacular in this image, is showing off its big spiral arms, which you can see reaching around the outer parts of the galaxy. You can see a lot of dust in these spiral arms, and you can see these kind of purplish hot spots. Formation is particularly active, and the bright light from those massive stars is ionizing the gas, giving us these beautiful colors. In the core, you see this glow of yellowish light. There's so many stars there that the starlight just kind of blends together. And around the center of this galaxy, we have a ring of particularly bright emission. This is caused when the conditions are just right in galaxies like this for intense star formation. So this galaxy is producing new stars at a high rate, and in particular in that ring around the nuclear part of the galaxy.
Yeah, it's really beautiful. We've got another image of a spiral galaxy, Caldwell 36. So Caldwell 36, it seems like we're almost missing a chunk of the photo here. So what are we seeing, Jennifer, or not seeing?
That's a good question. So first of all, you see that it's a beautiful spiral galaxy, another case of just a marvelous windmill type pattern of spiral arms with lots of stars. star formation, dusty regions. That kind of stair-step shape in the upper right is actually an aspect of the camera that was used to take this image. The Wide Field Planetary Camera 2 is almost like having 4 cameras in the 4 quadrants of this. And the upper right quadrant, that camera actually can see things in higher detail than the other 3 quadrants, the other 3 cameras. So if we want it all to kind of be at the same resolution, we have to shrink down the image from that upper right camera or that upper right quadrant so that it matches the same resolution capability of the other 3 camera pieces. And when we shrink it down, it kind of gives us this resulting stair-step pattern in the final image. But if you can kind of ignore the stair-step pattern, you can see the gorgeous, gorgeous central part of this galaxy and the spiral arms around it. And again, another example of nature's spectrums of arranging stars and continuing the production of new stars in active spiral galaxies like this one.
Yeah, thank you, Jennifer. We've got another beautiful galaxy image of Caldwell 29. So at the heart of Caldwell 29, astronomers suspect that there is a supermassive black hole. So Michelle, could you tell us more about what black holes are?
Oh, absolutely. So, I mean, the amazing thing about a black hole is that it's a region of the universe where gravity is so extreme, it can actually suck light in itself, and that's why we call them black holes. Now, normally we think of black holes being formed by stars that die and their cores collapse under the force of gravity. But in this case, we're talking here about a supermassive black hole. In the center of a galaxy, black holes can get to millions or even billions of times the mass of our sun. So this galaxy has a particularly mysterious, bright center. And although we're seeing visible light here in Hubble and maybe a little bit into the ultraviolet and infrared, what we also measure from this galaxy is X-ray light. X-ray light is only naturally produced when the gases reach temperatures of over millions of degrees. So as things fall in closer to this huge black hole, they get caught by the black hole's gravity and accelerated faster and faster around, almost like water going down a drain. All of that friction heats the gas up to millions of degrees, and it flickers on and off in X-ray light. So in the core of this galaxy that you're looking at here, there is a monstrous, huge black hole. And one of the big mysteries that Hubble and other telescopes are trying to solve right now is how black holes can actually grow that big. Millions or billions of stars must have gone into that black hole.
Wow. So the Caldwell catalog also contains something called planetary nebulas, like this image of Caldwell 56. But the term planetary nebula is a little bit misleading. So Michelle, what are we looking at?
Well, sure. So here we're looking at something closer to us. When you look out to galaxies, you're looking at things that are millions or tens of millions of light years away. In this case, this is a nebula, a glowing cloud of gas that's in our own galaxy, about 1,600 light years away. And as you mentioned, we call these planetary nebulas, but unfortunately that name was picked before we really understood what they were. We saw all this glowing material around a star, and we thought, hey, maybe there are planets forming. But instead of the birth of a solar system, what we're actually looking at here is the death of a solar system. Planetary nebulas are formed when a star begins to die, and it bloats up to huge sizes, then begins to drift away into space. And what's left at the very center of this nebula is a white dwarf star, a star that's actually just lost its nuclear reactions entirely and is slowly cooling off. So this is a wonderful planetary nebula that it's a little bit poignant. We're actually looking at the death of a solar system. And that's the gases that you see glowing here being unraveled from this dying star.
Very cool. Thank you, Michelle. So the next cosmic object we're going to look at is Caldwell 73, which is a globular cluster. You can find Caldwell 73 in the southern skies with binoculars. But Michelle, what exactly is a globular cluster?
Oh, these are absolutely wonderful. These are the largest star clusters that are part of our galaxy, the Milky Way. They orbit around the Milky Way, but not actually usually in the disk of the Milky Way. We are in this disk of gas and dust going around. The globular clusters are going every which way around the Milky Way, sort of like a swarm of angry bees, and they are huge. This particular globular cluster, the center of it is about 40,000 light years away from the sun. And it has the mass of over 500,000 suns. And because we think that most of the stars in this globular cluster are actually not as massive as the sun, that means it probably has 1 million stars or more.
The amazing thing about these globular clusters is they're also very old. So this particular cluster we estimate to be a little bit over 9 billion years old. And when you think about the sun being somewhere between 4.5 and 5 billion years old, this is an old cluster indeed. So these clusters may give us clues about how the galaxy formed and even what the universe was like many billions of years before the sun and the earth formed. So it's absolutely lovely. I mean, doesn't it look like sort of scattered diamonds and jewels on black velvet? You know, I've had the privilege to be looking at this cluster in the southern hemisphere, and even through a small telescope, it is absolutely spectacular.
Yes, it definitely is. Now, one of the coolest things about Hubble is that it can look at cosmic objects in different wavelengths of light. So let's take this image of Caldwell 52. Hubble was able to image this galaxy, this elliptical galaxy, in both visible light and infrared. So Jennifer, when Hubble is looking at an object in the infrared, what is that telling us?
Well, we are so fortunate that Hubble is able to look at objects like this galaxy with different kinds of eyes, if you will. Certainly we can look in visible light, but Hubble also has the capability of taking in ultraviolet light, which is bluer than blue, and also somewhat into the infrared part of the electromagnetic spectrum of light, so redder than red. When Hubble looks at visible light, it's capturing starlight in visible light, and also sometimes you can see regions where dust in the galaxy is blocking out some of that starlight. So you can kind of see the blockage there. When we look in the infrared part of the spectrum using Hubble's infrared capabilities, we can see more of the reddish stars throughout the galaxy and more of the emission coming from dust throughout the galaxy as well. Kind of the glow from dusty regions, heated regions. And if we can combine what we see in infrared light with what we see in visible light, we get a much richer picture of what we're seeing in that galaxy. We can learn a lot more. So in the Hubble image, you can actually see the infrared picture up in the top middle, the visible light in the bottom, and the combination of the two in the upper right. And you can see how much we can see and learn a lot more by having both visible and infrared light combined.
Definitely. And Jennifer, even after 30 years, Hubble is still bringing us amazing views of the universe. So could you tell us what this landmark anniversary means for the mission?
Well, we are delighted that the Hubble Space Telescope is working very well, even though it's been operating in space for 30 years. It's a satellite in orbit around planet Earth. It was launched and deployed by the Space Shuttle back in 1990. And thankfully, we've had several return visits from astronauts to the Hubble Space Telescope over the years. Each time astronauts have returned to Hubble, they've been able to repair things or install new and improved instruments, including science instruments. So we now have on Hubble a really fantastic suite of cameras and spectrographs. We have good gyroscopes and batteries that help us be able to operate the telescope and point it accurately. And we're confident that the Hubble Space Telescope will be able to operate well for quite a few years to come, hopefully throughout most of this decade and maybe beyond. And that's good news for science, because Hubble right now is really at the peak of its scientific capability, even 30 years into its mission. We're doing things with Hubble now that we hadn't even imagined before it was launched, like studying the atmospheres of exoplanets, planets orbiting stars other than our sun, outside of our solar system. And we're looking ever more deeply into the universe at distant galaxies as well, understanding the history of the universe. We are also looking forward to Hubble operating in complement with the James Webb Space Telescope that is due to launch the latter part of next year. When Webb launches and operates, it will be a wonderful telescope that's very adept in the infrared part of the spectrum, looking deeper into the infrared than Hubble can achieve, whereas Hubble can see visible and ultraviolet light that the Webb telescope won't see. So in complement, these two observatories will be a very powerful tool for understanding distant galaxies, the early universe, and also star and planet formation in our nearby our own galaxy as well. So we're very excited to celebrate Hubble's 30th birthday, both for looking back, but also for looking forward to what we're going to learn about the universe in the coming years.
Fantastic. So if you're just joining us, we're live and talking about newly released Hubble images of objects from something called the Caldwell Catalog. The coolest part about the Caldwell Catalog is that you can find these cosmic objects in the night sky with telescopes, or sometimes even with just binoculars or your eyes. But what exactly is the Caldwell Catalog? Joining me now, we have Hubble's Science Operations Manager, Kevin Hartnett, and our lead science writer, Vanessa Thomas. They're also both amateur astronomers, which means they use their own telescopes to look at the night sky. So Vanessa, you were responsible for pulling together this collection of images. Could you tell us what the Caldwell Catalog is and what its purpose is?
Yes, of course. The Caldwell Catalog is a collection of 109 celestial objects, galaxies, star clusters, and nebulas that, as you said, can be seen with amateur-sized telescopes, and sometimes they are bright enough that you can see them with binoculars or even the naked eye. And the collection was put together by a man named Sir Patrick Moore, and he was a British amateur astronomer and science communicator, and he put the collection together for fellow amateur astronomers to have some targets to look at with their own telescopes. He found these objects interesting and wanted to share his list with others, and it was inspired by a more famous catalog that was put together even earlier called the Messier catalog that was put together by a French astronomer, and that also included galaxies, star clusters, and nebulas that amateurs can see with their own telescopes. The difference between the two catalogs is that Messier's catalog included only objects that could be seen in the northern hemisphere, where the Caldwell catalog includes objects that can be seen in both the northern and southern hemispheres. So wherever you live in the world, you can see some of the Caldwell catalog objects.
That's awesome. Thank you, Vanessa. So Kevin, speaking of finding these Caldwell objects in the night sky, you actually took an image of Caldwell 14, which is the double cluster in the constellation Perseus. Let's go ahead and take a side-by-side look of the image you got and the image that Hubble has. Both images look amazing. So could you tell us a bit more about them and how people could find Caldwell objects in the night sky?
Sure. Well, Caldwell 14 is an amazing object, and this is a great time of the year to see it. It's located in the night sky between the constellations of Cassiopeia and Perseus, and is frequently called the double cluster in Perseus, and you can see why. With a small telescope from a dark site, you can see basically what I've imaged here. Two distinct open clusters of stars, each with hundreds of glittering members. It's really an unforgettable sight. If I could have the next graphic. This graphic shows the location of Hubble's image in the greater context of the double cluster. One thing stands out immediately. Hubble's field of view is tiny compared to the size of the double cluster. It would take Hubble Space Telescope hundreds of images all stitched together to form a big mosaic to capture all of Caldwell 14. This is one of the reasons why NASA is preparing the W1 mission, because this space telescope with one shot will take all of Caldwell 14 with the resolution of the Hubble Space Telescope. Now, how do we find the Caldwell objects in the night sky? Well, if you don't have a motorized go-to telescope, you'll need different things. First, you'll need a good listing of the objects and some detailed star charts for where to find them. Now, these thankfully are easily available online or in an atlas or even in a phone app. Second, you need a dark spot. Get out away from city lights if you can, and let your eyes dark adapt to the night sky, and you'll begin to see those fainter stars and constellations that you can't see from the city location. It's helpful at this, in this regard, to go out on a night when there isn't a bright moon in the sky. Then you need to choose your optical aid based on the brightness and the size of the object that you're looking for. So again, you can use anything from binoculars like these 7x50s, which are great, or a small telescope like this 3.5 inch here, or for some of the fainter objects, something in a 6-inch class like this one here. So the final thing is really to remember patience and persistence. This is a treasure hunt. And imagine what it's like to see with your own eye in the telescope the light from a distant galaxy that's millions of light years away. It's really worth it. It's unforgettable.
Thank you so much, Kevin. Before we jump into some audience questions, let's check back in with Vanessa. So Vanessa, there are more images and information about the Caldwell catalog online. So could you tell us more about what we can find on Hubble's website?
Absolutely. If you go to nasa.gov/Hubble, you will find a link to our Caldwell catalog, and there you'll find some background information about the catalog and Hubble's images of these objects, and you'll see a gallery of all of the objects in the Caldwell catalog that Hubble has observed and we've released images of. And you'll see some of the new ones highlighted in new. And if you click on one of those objects, you'll get the full image. And you may even see more images than just one, because sometimes Hubble has seen more or taken more than one image of an object. And you'll find some information about that object as well as how to observe it. You'll see a basic star chart that'll give you an idea of where the object is located in the night sky, and it'll tell you what constellation it's in and what time of year to look for this object. If you look at the description, it'll give you more detail about whether it's in the northern hemisphere sky or if it's in the southern hemisphere sky, and whether you need a telescope or binoculars or if you can see it with naked eye.
Great, thank you. All right, now we're going to take a look at some questions. We have one from Facebook. Okay, so what can Hubble tell us about elusive phenomena like singularities and gravitational distortions? Jennifer, would you be interested in that, or Michelle? Feel free to jump in.
I can take a shot at it. We are able to see the effects of some of these unseen phenomena. So let's take dark matter, for example. We now know that the majority of mass in the universe is unseen. It's dark matter, but we know it's there because of its effects, its gravitational effects. One of those effects of dark matter is to actually distort space-time. All mass actually can do this. And if you have a lot of matter together, such as in a cluster of galaxies, there's a lot more dark matter than the visible starlight. And that can actually distort space-time significantly enough that when we look at that region with the Hubble Space Telescope, the light coming through that distorted region from a background galaxy will get magnified and distorted, stretched out. Sometimes we'll see multiple apparitions of that background galaxy. We call this gravitational lensing. And through it, we're able to discover and detect and map out the distribution of dark matter in that cluster of galaxies, even though we can't see the dark matter. And we can also learn things from the background galaxies that are very distant but are getting magnified by this effect. So that's one of these sort of unseen phenomena that Hubble is very good at studying, because we can see its effects through gravitational lensing. We're also contributing to the study of dark energy. This is the mysterious force that seems to be propelling the expansion of the universe to faster and faster rates. Hubble, as well as telescopes on the ground working together, were used to actually determine that our universe is not only expanding but accelerating, and we're using these telescopes to get a more precise measurement of that rate of expansion of the universe now and the history of that expansion over time. We don't yet know exactly what dark energy is, but Hubble is giving us a lot of new information to help us find out.
Great, thanks, Jennifer. Okay, one other question we have. So are these actually photos taken by Hubble as it is, or is it like a reconstruction of raw images? So maybe if someone wants to talk about how we get the Hubble images that we see today briefly. Let's see.
I vote Vanessa.
All right. Sounds good.
I can take that. So Hubble takes images in black and white, actually, through different filters. So it uses filters to isolate the type of wavelength that astronomers want to observe. So Hubble's images actually come down black and white. And to get color images, we have to take multiple images, exposures, in multiple filters. So we put those multiple filter images together to create these beautiful color images that you see. And yes, and we do additional processing. Sometimes Hubble takes multiple images of an object because maybe the object is too large to fit in the field of view. So we have to take multiple images to get the whole object or to get more of the object of interest. And so we have to mosaic those images together as well. So there is some processing that goes on, yes.
Gotcha. Thanks, Vanessa. Awesome. Okay, so on Facebook, it sounds like we have someone who is a beginner amateur astronomer looking for some tips. So Kevin, do you have any words of wisdom?
Well, my best tip for folks that are getting into astronomy is to find a friend to do it with. Now, one has to be careful these days because of COVID, of course, to be in a group doing this, but there are clubs, many clubs out there for amateur astronomers. And if you join a club, which meet virtually now, you can learn a lot about different types of telescopes, different tricks to observe, and it's all very helpful rather than trying to do it alone. So that's really perhaps the best tip that I can give you. Don't do it by yourself, or if you feel like you have to because of COVID, take advantage of online meetings or YouTube videos. There's lots of them out there that describe telescopes or binoculars and how to use them. There's a wealth of information online these days.
Great. Thank you, Kevin. All right. I think we're just going to do one more from Facebook. How far away is Hubble from us? So anyone want to take that one on?
I can take a jump at it, but it's about 300 and it varies actually, but varies between about 340 and 360 miles above the surface of the Earth. Over the years of its mission. It's not that far away from the surface of the Earth. It's in low Earth orbit, again, not to get it a lot closer to the things that we're trying to observe with Hubble, but to simply get it above much of the Earth's atmosphere so that we don't have to look through that turbulent atmosphere that can actually blur the images that we're trying to look at. And also the atmosphere of the Earth actually filters out some of the light that we want to capture with Hubble, like ultraviolet light. So it's not very far up. It was deployed there also because that's where the space shuttle could go. And we wanted to use the space shuttle to take the Hubble up into orbit and to return to visit it several times. You should note, however, that a lot of telescopes now in space, and there are other space telescopes now and also in the future, are not being put in low Earth orbit. Some of them are being put much farther away. The James Webb Space Telescope, to be launched next year, the latter part of next year, will be 1 million miles away at a place in space called L2 that is quite far away. We want to keep the Webb telescope very cold. We want those sun shields that you see in the image there protecting the telescope from sunlight and heat to be effective. And we want to be able to have the most sensitive infrared observations possible. So that's why the Webb telescope will be put much farther away from Earth than Hubble was put.
Absolutely. I think we do have time for one more question, and maybe Michelle can take this one. Speaking of James Webb, which is coming next year, is Hubble getting upgraded after James Webb, or what are we looking at with the future of our space telescopes?
Well, right now there is actually no plans to visit Hubble with the astronauts again, and part of that is because we don't have the space shuttle. So Hubble is not actually in the correct orbit. The space station, for example, is in a very different orbit than Hubble. So we hope that Hubble keeps working as well as it is now, maybe even for a decade. The last mission that went up there in 2009 replaced a number of the cameras. So the cameras are actually much younger than 30 years, just a little bit more than 10 years old. And they also did things like replace gyroscopes so that the telescope will be able to point itself very well. So, some of the things that I'm really excited about as far as what we're doing in the future of Hubble, we're working on, for example, catalogs that astronomers all around the world can use, catalogs of say, star regions where young stars are being formed right now. Another thing that we're doing that I'm very excited about is monitoring the atmospheres of planets like Jupiter and Saturn. So a lot of people have heard that the red spot of Jupiter is shrinking. It's actually changing color as well. So Hubble will be doing that too. So Hubble has a huge future ahead of it. And although we're not expecting to actually upgrade it at this point, it is still going to be this incredibly relevant and wonderful observatory. And when the James Webb Space Telescope is launched later next year, the two observatories, we hope, will be able to work in conjunction to some degree. And this will allow us to do something called calibration, where we make sure that one telescope is agreeing with the other telescope. We can make our images and our measurements as accurate as they can possibly be. So that's something I'm looking forward to next year. It's going to be a big event.
Yeah, it's going to be awesome. Well, thank you all for sending in these questions. Unfortunately, we're going to have to wrap things up for today, but if we didn't get to your question here, we'll try to answer it later on social media. Thank you for joining us. We love sharing these newly released Hubble images of objects from the Caldwell catalog with you. All the images we talked about and many more can be found online at nasa.gov/Hubble. There, you can also find more Hubble content and fun online activities you can do with your family or on your own. Be sure to keep up with us on social media at NASA Hubble on Twitter, Facebook, Instagram, and Flickr. Thanks again for joining us, and have a wonderful weekend.
Without the shuttle going up to replace any equipment failures that we have, we have to make do with what we have. What we really are concentrating on is just keeping the telescope working and keep the science going.
And everything looks excellent, and we have no reason not to expect that Hubble will last until the late 2020s and beyond.
My name is Mike Wins, and I'm the lead systems engineer for what's known as the Optical Telescope Assembly of the Hubble Space Telescope. I'm in charge of what's known as defined guidance sensors. These are the instruments that actually help Hubble do the exquisite and precise pointing that it does. Right now we're getting ready to perform an observation. The telescope is going to be trying to go to acquire some guide stars in just a few minutes here. The stock is the Space Telescope Operations Control Center, where we send commands to the spacecraft. On a daily basis, we have to send up what's known as command loads.
Accepted. DCMR is good. Step 3 is complete.
Because the computers on Hubble are very old and they have very little memory, in fact, most of your memory sticks today are 20, 30, 100 times bigger than Hubble, we have to send up essentially a load of all the commands Hubble's going to be doing for the next 24 hours.
On a routine basis, we always keep 24 hours of instructions on board, so it's routinely updating for the new sequence 24 hours in advance.
We'll start with doing our premise uplink.
Hubble is always working, it's always doing something, it's always doing some sort of observation or calibration or getting ready for the next task.
We'll be logging on forward at 14:33:17.
Hubble is truly a 24/7, 365-day-a-year instrument, so the Hubble can keep on going. It never stops.
And we are configured. It's been verified.
Now we do have to, because of this low Earth orbit we're in, the actual observations, when we're taking a picture of something or doing a science observation, we actually have to wait because sometimes the Earth gets in the way. So we have to pause, wait until the Earth gets out of the way as we go back around and start the observation back up.
You have constraints. You don't want the optics pointing at the sun, and you don't want the instruments to have their shutters open when you're looking at the Earth, because the Earth is bright for them. And then we have the South Atlantic Anomaly, the SAA, which is a portion of the Earth where we get proton hits that will affect the electronics in Hubble and can also affect the instruments in Hubble. And so we have to plan out very carefully our targets and observations. We have a timeline that's laid out to maximize the efficiency of it.
Hubble can actually take observations during day and night passes. Every 95 minutes, we go around the Earth. The batteries will charge from the solar rays during the day pass, and then at night, batteries power the observatory so we can continue observing. The scheduling with Hubble, we're trying to put it together as efficiently as possible, minimize our gaps. The goal is to constantly keep it busy.
We're constrained to a certain extent, but whenever we have visibility, we are observing.
The demand for use of the Hubble Space Telescope from scientists around the world is very high.
Hubble is at its most productive. It's got some of the best instruments that have ever been on board it. There's a very high demand. Hubble's performing exceptionally well.
2, 1, and liftoff of Space Shuttle Atlantis. The final visit to enhance the vision of Hubble into the deepest grandeur of our universe.
Since the final Space Shuttle servicing mission, we're using Hubble to get the best kind of science return we can from the suite of instruments that we have. So our focus now is on making sure we get the best science while it's still operating so well.
Luckily, at the end of the last servicing mission, we were actually left with a telescope in great condition, but Hubble is getting older and older. It's a very old telescope.
Now, 10 years after the last servicing mission, we can't rely upon servicing missions to fix things, so we have to rely upon our own ingenuity to be able to figure out if something does fail, what are the alternative paths that we have.
For the telescope to keep giving us this peak science, we need lots of things to be working together very well on the telescope. We need a pointing accuracy system that is outstanding and keeping that whole system healthy and functioning so that we can point Hubble very accurately even while it's whizzing around Earth in its orbit.
For the telescope to be able to do the science it needs to do, we have to hold it very, very steady. There is actually a little bit of motion. I mean, it's hard. We're zooming around the Earth at 17,000 miles an hour, so it's hard to hold the telescope perfectly like that. The gyros are working really good.
The gyroscopes can sense motion in each direction. And so because of the gyroscopes that we have on board and how sensitive they are in terms of sensing motion, that we can keep our cameras steady.
Gyros are very good at measuring these very small rates. The fine guidance sensors are actually sort of used, I always like to describe it as backseat drivers. And they constantly tap on the gyro's shoulders, it's about once a second. And they keep saying, turn left, a little bit more right, a little bit left, a little bit right. I mean, it must be driving the gyros nuts. So the fine guidance sensors allow you that really fine control, but actually it's the gyroscopes driving the telescope. And they're doing a perfectly good job here. Everything looks good, our stars the right brightness. The reason that is because we need to make sure we have the correct guide stars. One of the things we look at is the brightnesses, and that's what we're measuring here. Those are about right for what the stars were. But also, we wanted to make sure they were exactly as far apart as we thought they were going to be. And it did. It did a check, and it passed a very, very tight tolerance check to make sure that those were the right stars. So we know we're locked up on the stars. We got a good lock here. The gyroscopes are very critical because to be able to move from one position to another position, the gyroscopes are the only thing that can tell us how we can do that. We have 6 gyroscopes on board Hubble. Currently, 3 of them are still working. And 3 is sort of what people used to think of as the minimum number, but we have developed a science mode where we only need 1 gyro.
A big part of our job is to make sure that we can extend the life of Hubble and continue doing the high performance science that we're doing for many more years.
And what we've done is we've gone through all the critical components of Hubble and said, how can we potentially make them last longer, as you might do with your own car that's getting more miles on it. The gyroscopes have been our most problematic piece of hardware, so I helped lead an effort to develop a 2-gyro science mode. And we were able to use that mode on orbit and be able to perform science. And then learning from that, we actually developed a 1-gyro science mode that we've been able to test on orbit, but we haven't been called on to use. But in the end, possibly 5 to 10 to 15 years from now, when we're down to potentially our last gyroscope, that is the mode we will be in. Before we do anything on orbit for the first time, we have to test it out on the ground. And we're very lucky to have what we call the VEST, the Vehicle Electrical System Test Facility. And the key with the Vehicle Electrical System Test Facility is it's an exact copy of the main part of the telescope where all the electronics are. And it has the mechanical bays, it has the computers, the electronic boxes installed in there, and it has the cables and harnesses in there. And in fact, when we were building the VEST, we had the quality engineers came to us and said, you're not doing these cables exactly the way you should be doing them. You know, we've got better standards now. And our thing was, we're trying to build a copy of what we have on orbit. And so what you have in the VEST is an exact electrical copy of the Hubble Space Telescope. every orbit as we come around the Earth to be able to get our attitude correct, to get ourselves steady and locked on. The fine guidance sensors and the gyroscopes are key to that. And that's why those are the two of the subsystems that are on the top of our list as far as having contingency plans for and monitoring the health and safety of those and making sure we have them in peak performance. When something fails on Hubble, or we have an anomaly, something we don't understand, one of my jobs is to bring together the experts, which may be a thermal engineer, a mechanical engineer, an electrical engineer, a software engineer, all these different people. And we'll say, you know, how do we deal with this issue? And how can we work around it and return back to peak science? What you do is you come up with a list of what is available to you on the telescope in terms of potential. I could close this relay or open that relay or turn on this box. And I am continually amazed. You have a telescope on orbit that you can't even see. And all you're doing is looking at the data coming down to you from the ground. These experts are able to use their ingenuity and come up with ways to continue to operate Hubble. And everything looks excellent, and we have no reason not to expect that Hubble will last until the late 2020s and beyond.
I personally am extremely grateful to the Hubble operations team, these people who work day and night to keep Hubble operating, providing exquisite science return, giving us the information that we need to know how Hubble's doing. Is it doing the kind of accurate pointing that we need? Is it getting the sensitivity in the various wavelengths of light in the various instruments that we need to have to do the science? Are we able to calibrate those observations in an accurate way? We couldn't do any of those scientific analyses if we didn't have this team of operations experts behind the scenes making sure that the details of Hubble's technical operations are being monitored, being handled, being managed, being planned in a near perfect way.
Things Hubble has been doing is looking at the atmospheres around exoplanets.
If you had asked the guys who built Hubble and designed Hubble, they would have sworn Hubble could never, ever do this.
That's one of the things I love about Hubble, is that it ends up giving us new questions, new mysteries to explore.
My name is Larry Dunham. I'm the Chief Systems Engineer for Flight Systems here on the Hubble Space Telescope. I started on the Hubble program back in the summer of 1982 when Hubble was being built out in California. First telescope in space to be designed so that we've got what we call orbital replacement units. They're modular boxes with handrails on them so the astronauts can go up and just pick and play. They've got nice connectors on them that make it easy for the astronauts with their big gloves to be able to put them in and out.
We've had 5 servicing missions. We have replaced some equipment multiple times, especially the instruments. We're always going with the advanced technology.
The telescope we have today on orbit is not the telescope that we launched originally. We've been able to replace all 5 of our science instruments with instruments that have the technology that didn't even exist when Hubble was being built originally.
The Hubble Space Telescope is really an observatory because it has several science instruments, several modes of operation. We have multiple cameras, multiple spectrographs. They each have different capabilities in terms of their sensitivities or the kinds of frequencies they can receive, the electromagnetic spectrum. We can also use Hubble in different kinds of intriguing modes depending on what we're trying to observe.
There are different types of observing scenarios, and one of the things the scientists have been able to do is they've been able to come up with very interesting and unique observing scenarios that allowed them to do science that they never thought they could do before.
Because the Hubble Space Telescope has been operating for a long time, it's giving us what we need to explore the universe in deep ways that would never have been possible when Hubble was first launched. For example, scientists wondered whether we could use Hubble in an innovative mode in recent years, basically scanning objects slowly instead of just staring at them. In some cases, that gives us a higher sensitivity to what we're trying to observe. And we're using that special mode on Hubble now to get better information about many types of things in space, including to be able to study planets around other stars, what we call exoplanets, planets outside of our own solar system.
What Hubble's been able to do is, as the planets go in front of the stars that they're going around, the spectrographs can detect changes, very small changes in the spectrum. This has allowed them to do exoplanet atmospheric studies. This is something that Hubble has sort of really stepped up to the plate and has been just phenomenally good at. Spectrographs have really sort of been leading that. If you ever see things about, oh, a new exoplanet was discovered that has this in the atmosphere or that in the atmosphere, or we think it's made of this, it's the spectrographs which have shown you that kind of information. For doing a lot of the exoplanet observations, you have to catch what's known as a transit. One, the orbit of the exoplanet has to be such that it's going to go between you and the star it's going around. We can't just do an exoplanet observation whenever we want or whenever it's convenient. We have to do an exoplanet observation when it's first starting to go into the star. And so they have to know very accurately the timing of that. We have to schedule it ahead of time. This is not something that Hubble can get around to when it wants to. We have to say, no, at this point in time, on this date, you have to be pointed here and you have to be looking here. We had to really think about how to schedule this. A lot of thought goes into it. A lot of thought goes into the planning and of the execution.
The Hubble operations team are quite willing and capable of using the telescope in new modes and new innovative ways that enable us to accomplish science that we wouldn't otherwise be able to accomplish. We asked them, would it be possible to use Hubble to track something moving quickly across the sky? And they figured out a way to use Hubble in a vast tracking mode that enable us to do explorations and discoveries that astronomers didn't envision using Hubble for when it was first designed.
Now, when we're observing our planets, when we're observing Jupiter or Saturn or Uranus or Neptune, they move also. We have to move the telescope because they're just going around the sun. They're actually moving because they're really moving. And so we have to move with them. We're observing asteroids or comets. We have to chase after them.
Oumuamua, we know came from outside of our solar system, is like a big asteroid that was detected whizzing through our solar system. We wanted to use Hubble to observe this as well, and we were able to track it. This is not a simple operation. It's moving at more than 100,000 miles an hour, so being able to observe this and track it is a wonderful capability that the operations team has enabled Hubble to have.
The telescope is big, it's massive, it moves about the same speed as the minute hand on a clock. So to move from pointing one thing to go completely around the other one takes us a half an hour. It is not a very fast motion. We actually use a very interesting technique. It's using Newton's third law. We have these very large reaction wheels on it. They're about 2 feet across, very, very heavy, very, very massive wheels. You start spinning those wheels one way, the telescope will spin a little bit in the opposite direction. This is how we can move the telescope from one part of the sky to another part of the sky.
Once we've moved the reaction wheels and we've moved the telescope so we're in the right spot, now we have to get in the exact location to put the target in the science instrument aperture.
What's going to happen now is the FGSs are going to start talking to the telescope, talking to the flight software computer and saying, I want you to move the telescope over here a little bit to be able to position the science for the science aperture.
Most of the time we use the Hubble Space Telescope to do observations that have been planned quite a bit in advance. Observers around the world, astronomers will write proposals. We will then take those accepted proposals and observe whatever it is that the astronomer has proposed. But sometimes there are things that happen that are unexpected or rapid events that we need a more rapid response.
We have a capability of what we call a target of opportunity. And that's when something unexpected happens in the universe that astronomers, they want to immediately jump on that as fast as possible with Hubble. Case in point was the gravitational wave detection to neutron stars colliding. A target of opportunity was submitted for Hubble to actually go look at the remnant and see if we could find it.
We had the engineers run through it. We got new commanding sequences from the Space Telescope Science Institute. We were able to run all that through, and then we executed on orbit.
We have to respond very fast. We produce a new schedule and set of command loads.
We can modify a lot of the flight software, modify how the instruments are commanded. It allows us to change. We can react very quickly. What Hubble has done compared to what we were thinking Hubble could do is just amazing. Hubble's had its fingers in almost everything, a neutron star collision, looking for all the supernova, all this stuff going on with dark matter, dark energy, exoplanets. Hubble has just been constantly finding new things. Now we're looking at these interstellar comets and these interstellar asteroids visiting us. It's really been spectacular to watch.
There really are two key aspects to Hubble's design that have enabled us to last the 30 years that we have, and that is really the redundancy that we have on board, and then it's the servicing, putting in new and improved instruments, and being able to improve the hardware with lessons learned over the 30 years of Hubble operations. We are now at our peak performance.
The Hubble Space Telescope has had a profound impact, not only on astronomy. It showed that humans in space and science can go hand in hand to enable us to explore space in richer ways than we could ever do with either just astronauts alone or just with instrumentation alone. By using these skills together, new vistas of exploration are open to us, and that lesson is something we're still benefiting from as we envision future space exploration.
Go ahead. Okay, we have a go for release. Okay, Charlie.
It's amazing with a program that's lasted the duration that Hubble has lasted, that the astronomers up at the Space Telescope Science Institute continue to come up with new things that they want to try to do with Hubble, and we certainly hope that we'll be able to continue to provide that kind of capability to them into the late 2020s and beyond. The further you look, the more you're going back towards the Big Bang and understanding how the universe was formed.
The Webb telescope will be groundbreaking because it has capabilities that are different than the Hubble Space Telescope.
We have equipment that is so much more powerful than anything we've ever had before that it's almost impossible to tell what we will discover.
Hubble's accomplishments include something called the deep fields, looking out into space and collecting light, sometimes for many days. These deep fields have revealed visually to us a universe absolutely teeming with galaxies, hundreds of billions of galaxies.
One of the neat things about the ultra deep field, and one of the things that made it so unique was how long it took us to take that image. There's an exposure time that's expressed, I think it's 11.2 days. There's a very, very long exposure time. But probably what's more important is how many orbits it took us to do that. 400 orbits of Hubble data to take that image. You only get 15 orbits a day. To take 400 orbits and say, we're going to observe this one spot in the sky for 400 orbits. And the really unique thing about that was they picked a spot where there wasn't anything. They looked and they said, there's absolutely nothing here. And they said, you want to spend 400 Hubble orbits looking at nothing? And they said, yes, because we want to see what it can see. And I think the results from the science, I mean, it was amazing. What they saw was spectacular.
Hubble had spent 2 weeks taking pictures of empty places in the sky, and they saw they weren't empty at all. They were thousands and thousands of galaxies.
We were amazed how many galaxies we've found, and we continue to go back to that portion of the sky to increase that visibility.
The Hubble Space Telescope is an outstanding time machine. It's incredibly important for our studies with the Hubble Space Telescope to realize that when we're looking at a galaxy, we're seeing it as it was millions of years ago, sometimes billions of years ago. It's taken that long for the light to get to us.
What you're looking at with a telescope, of course, is the light from billions of light years away. So the further you look, the more you're going back towards the Big Bang and understanding how the universe was formed.
What Hubble has revealed is that the universe has in fact changed over these billions of years of time. The early galaxies, the very distant ones as we see them, are simple. Sometimes they're messy looking, they're small, they haven't had time yet to form that grand spiral structure. Over time, we see galaxies actually merging with other galaxies and growing bigger and bigger, and those mergers can look like train wrecks in our Hubble images.
These very, very deep exposures that Hubble has been able to take, we have seen right to the edge of the universe, 13.5 billion years. When Hubble was first designed and envisioned, it was never thought it could actually see that far out. But because of the advances in the instruments that we've been able to put up on the telescope, and also the cleverness of the scientists, they've come up with very interesting observing scenarios, doing these really deep exposures where we just sit there for orbit after orbit after orbit, gathering the photons. We've been able to push Hubble out very, very far.
As Hubble looks out into these fields of galaxies, we sometimes see clusters of galaxies. These are galaxies that are held nearby each other by their mutual gravity. These clusters are massive conglomerations. There's so much mass that they have an actual observable impact on space-time itself. Einstein predicted that mass distorts space, but we didn't realize we could actually see the effects of that. But with Hubble, we have been able to see distortions in space around clusters of galaxies. The way we see that is when light from a background galaxy travels through that cluster of galaxies or around it due to this gravitational lensing effect. The lensing also magnifies that background galaxy, so if we look in some of these distorted arcs, we can see more detail than we would ever have been able to see without gravitational lensing, nature's boost.
There are observations where we're explicitly looking for the lensing, and they're getting science out of that just otherwise would just not be doable. Hubble has really taken that to a next level. It's doing large amounts of astrophysics that it's just never been able to do before.
Some of what we're doing with Hubble is to prepare for the new James Webb Telescope, which we anticipate launching in 2021, which will be able to see farther into the infrared part of the electromagnetic spectrum. That enables us to see some galaxies that are difficult for Hubble to see because they're so far away that their light is traveling through us through expanding space and gets stretched out into redder wavelengths, often far into the infrared part of the spectrum, even sometimes beyond what Hubble is able to detect well. The Webb telescope will give us more information about some of those very distant galaxies.
The James Webb Space Telescope is the follow-on telescope after the Great Hubble Telescope. It extends the discoveries of Hubble into the infrared spectrum region. We think that the first objects that grew out of the Big Bang material probably happened in about 100 million years after that start. And we think the Webb telescope can pick them up. They're rare, they're hard to find, but they should be there. The farthest we've been able to see with the Hubble telescope goes back about 800 million years after the expansion began. So we think we get much closer to the first objects with the Webb telescope.
Hubble gives information that the Webb telescope cannot give about visible and ultraviolet emission from things in the universe. And when we have all that information coming in at the same time, it's like a banquet of scientific return.
Now when we get the complete picture of every wavelength you can possibly see from ultraviolet to infrared, we hope to have the story of the growth of the first galaxies from the primordial material. So that will be a huge accomplishment that depends on both pieces of equipment, the Hubble telescope and the James Webb telescope working together.
So astronomers are very excited about this probability that we'll have both the Hubble Space Telescope and the Webb Telescope operating at the same time for quite a few years. That will give us an abundance of new understanding about the universe. And already right now with Hubble, we're doing preparatory observations for the Webb Telescope. We're using Hubble to do things, for example, like surveying distant galaxies to find out which ones would be prime targets for the Webb Telescope. In fact, scientists around the world are proposing observations with Hubble right now specifically to help us learn information that will be useful for making the best use of the Webb Telescope as soon as it's launched and gets going in its science observations.
I think the Hubble telescope has been the most productive science instrument ever built. In astronomy, there's what we knew before Hubble, and now there's what we know after Hubble. They're so different. Of course, Hubble has now had a life of 30 years, so it's had a long time to make this revolution happen. So it's not all at once. It's a gradual revolution, but it's still a huge revolution. Technology has changed dramatically over the 30 years of life of the Hubble telescope. So you couldn't even have imagined when the Hubble was launched that we would have the wonderful cameras and spectrometers that we fly today. We figured out how to send astronauts, we trained the astronauts, we figured out what instruments could be put in, we figured out how to repair everything that went wrong on the Hubble, and it's still alive. It's today, 30 years after launch. And I am so thrilled to say that our people were able to do that. That's the operations team that makes this possible. It's a miracle as far as I'm concerned, because it didn't have to be that way, but they made it happen.